So on this slide, we're making the connection between fluid and electrolyte, okay? Fluid and electrolyte. And this is a relationship that I've been stressing, right? The fact that water follows sodium. And so if we increase our solute reabsorption, we therefore increase this osmotic pull for water to follow, right? Water follows sodium. And so we want to talk about these three hormones that we've spoken about before, but some of their other roles in connecting that water and sodium balance, that fluid and electrolyte balance. So I've put here in brackets also because I don't want you to confuse this, right? Students often confuse this as being the primary function of these hormones. These are not the primary function of these hormones. We've already talked about the primary functions of these hormones. But what we want to make is the connection between some of the secondary functions of these hormones that connect sodium and water balance, right? So ADH we've talked about extensively. We looked at ADH. Its main job was to increase water reabsorption, right? Inserting those aquaporin 2 channels into the apical membrane and facilitating the movement of water from the tubule into the blood. So the main role of ADH is increasing water reabsorption. But ADH also increases the number of sodium channels in the apical membrane of those cells. Meaning that although the primary role of ADH is to increase water reabsorption, ADH also facilitates sodium reabsorption. And that's the connection between water and sodium that we're trying to make here, right? Wherever water goes, sodium follows. So if something increases water reabsorption, as a part of its secondary job, it's also going to increase sodium reabsorption. Likewise, angiotensin 2 and ANP, their main role was for sodium balance, for sodium regulation. We talked about angiotensin 2 as increasing sodium reabsorption, and we talked about ANP as decreasing sodium reabsorption. But they also have a role to play in ADH as well, in ADH secretion as well. And because they play a part in ADH secretion, they are also playing a part in water reabsorption. So angiotensin 2 increases ADH secretion, and in brackets here in your notes, you can put increases water reabsorption. We know the role of ADH is to increase water reabsorption. Whereas ANP decreases ADH secretion, and so ANP also decreases water reabsorption. And so the connection I want you to make here is that anything that increases ADH secretion, anything that increases sodium reabsorption also increases water reabsorption. And anything that decreases sodium reabsorption also decreases water reabsorption. Again, that connection between sodium and water, right? If we're moving sodium, water will follow. So these hormones that influence sodium reabsorption, such as ADH, also influence water reabsorption, and the reverse is true for these hormones that influence ADH reabsorption. ADH secretion, which is water reabsorption, they're gonna also influence sodium reabsorption. Okay, those two things are tied together hand in hand. All right, this is often a confusing slide, so I'll pause here to see if there are any questions, but hopefully putting also in brackets here kind of clarifies that confusion. Alrighty. Okay, so we can also speak about the response to hemorrhage. So a part of the physiologic response to hemorrhage or to losing excess blood volume is one, to decrease the blood volume, which is decreasing the mean arterial pressure. Two, we're going to increase the neurocontrol to the heart, right? Remember that baroreceptor reflex. If we decrease our mean arterial pressure, we're going to decrease stretch on those baroreceptor reflexes. That is going to send a signal to increase the heart rate, increase the stroke volume in order to correct that mean arterial pressure. And then a third response is going to be a more long-term response, which is controlling the blood volume by secreting ADH. ADH, as we just explained extensively, is going to facilitate water reabsorption, also helping to correct that blood volume dysfunction. And then the renin, angiotensin, aldosterone system, which is facilitating sodium reabsorption, again, in an effort to help correct that drop in blood pressure and to raise the blood pressure and restore the mean arterial pressure. So the hormonal control here is doing two things. ADH secretion, which is facilitating water reabsorption, but also the RAS system, which eventually results in aldosterone secretion, which is facilitating sodium reabsorption. Again, that water-sodium connection, which helps to restore blood pressure, okay? That connection I talked about earlier with sodium, water, blood pressure, right? Sodium, water, blood pressure. All right, and then the second objective we're gonna go on to is speaking about the influence of the acid-base balance, and then talking about those buffers once again, and then how the kidneys and lungs work to correct any of those disturbances. So this slide is a lot of repetition from what we talked about, right? This window that the pH needs to be at, the fact that if we go outside of that pH window, we can end up with some really significant physiologic complications. That is because we denature proteins, and we talked about acidosis as being a state of depression of our nervous system, alkalosis as being a state of excitability of our nervous system. But we also want to make the connection to potassium balance, okay? So if you're in a state of acidosis, automatically that puts you at a state of hyperkalemia, okay? Excess hydrogen ions facilitates excess potassium ions. Whereas if you're in a state of alkalosis, that puts you in a state of hypokalemia. Decrease in hydrogen ions creates a state of decrease in potassium ions, because hydrogen ions and potassium ions kind of go with each other, right? Potassium loves to follow those hydrogen ions around. So if you lose acid, you lose potassium. If you have excess acid, you have excess potassium. And so this is why we need to keep our pH balance. This is another reason we need to keep our pH balance, because we also need to keep our potassium balanced. If we have potassium going out of balance, this can put us in some other physiologic complications, such as cardiac arrhythmias and vasodilation. In fact, if any of you have ever heard of, I forget what they call it, a lethal injection. So the lethal injection, which is a part of capital punishment. So if you are sentenced to die via lethal injection, a part of that process is administering potassium. So potassium concentration or potassium solution is what the lethal injection is, right? If you have excess potassium, this can create a situation where you disrupt the electrical activity of the heart and the heart pretty much stops, right? So that is how deadly excess potassium can be, and this is why it's important to regulate acid-base balance, because acid-base balance then has consequences for potassium balance. Alrighty. So here we can see some of the inputs of acid to our physiology, right? We've got proteins, which are acidic in their nature. We've got fats, which are acidic in their nature. And so the more protein and the more fat we intake in our diet, the more acidity we put into our blood. Likewise, we have metabolic processes which are releasing these acidic byproducts, carbon dioxide being one of the major byproducts of cellular respiration, lactic acid being a byproduct of muscle metabolism, and then keto acids being a byproduct that is quite acidic as well. So if you're not using glucose as your main source of fuel, let's say you're on a ketogenic diet, or if you're using mainly fats as your fuel, the breakdown product of fats is these keto acids like hydroxybutyric acid and so on, and they are quite acidic. So these are the things that contribute to having quite an acidic state in the blood, and so we need to balance these through the kidneys and through the lungs. So the kidneys have the ability to secrete hydrogen ions and lose it in the urine, and the lungs have the ability to blow off excess CO2, again losing it through excess ventilation, blowing it off through the lungs. And so these are two ways that we can lose some of the acidity that may begin to build up in the blood. And we talked about some of the different trends of the kidneys. We talked about some of the ions that were secreted. Let's go back to this slide here. So in one of our previous packets, we talked about this table. And I didn't stress too much on you memorizing these, but I talked about the trend that shows up in terms of what's being moved across what part of the tubule. And we talked about the ability for the proximal tubule, the distal tubule, and the collecting duct to secrete these hydrogen ions. That is to lose it into the urine, to lose it into the tubular fluid. And so this is a part of that acid-base balance, the ability of the kidneys to secrete hydrogen ions and to lose that excess hydrogen, which is acid, into the urine. Another trend that I pointed out was the ability of the proximal tubule to reabsorb a lot of the important substances, and bicarb is one of those important substances. So the ability of the proximal tubule to reabsorb bicarbonate is another way that the kidneys can regulate our acid-base balance. So basically the kidneys can lose excess acid by secreting it into the urine, or it can reabsorb base, right? Bicarbonate is an alkaline substance or a basic substance. And if we reabsorb that, we can also help to regulate our acid-base balance. Okay. So let's talk about some of the sources of acid-base disturbances, basically how we can cause these disturbances. First off, we want to understand that carbon dioxide is a biologic acid. I keep mentioning that. So if we change our rate of ventilation, we can change our rate of losing or holding on to acid. And so the lungs and our breathing rate is one way of bringing about these acid-base disturbances. And we talked about these a little bit earlier in this packet. And so we want to maintain our respiratory rate by maintaining the respiratory chemoreceptor reflex. And if we do not do that, right, if we have any type of acid-base disturbance, the lungs can cause those disturbances, but the lungs can also work to correct disturbances, okay? So if you have acid-base disturbance, let's say you have an excess diet that has lots of fats, lots of proteins, and so you have more acid coming into your system, this is going to be a trigger for these respiratory centers, these chemoreceptor reflexes that pick up that excess acidity in your blood, and they are going to trigger the lungs to increase your ventilation to blow some of that CO2 off. So whereas the lungs can create acid-base disturbances, the lungs can also work to correct acid-base disturbances as well. And so if we increase our plasma CO2, we're going to be in a state of respiratory acidosis, holding on to that acid or that CO2. And if we decrease our plasma CO2, we're going to be in a state of respiratory alkalosis, which is losing too much of that acid and putting us into an alkalotic state. Let's speak about the metabolic disturbances, okay? So earlier I talked about the fact that if it's being created in the lungs, we call it a respiratory imbalance or a disturbance. If it is being created anywhere outside of the lungs, so in your diet, if you're doing lots of exercise and generating lots of lactic acid, any cause of a disturbance that is not created through the lungs, we're going to call it a metabolic disturbance. And so we can speak about a metabolic acidosis as a state of gaining excess hydrogen ions or losing excess bicarbonate ions. And this can be brought about by a few different ways, but not through the lungs. So anything other than CO2 will contribute to a state of metabolic acidosis. That can be a high protein diet, that can be a high fat diet, lots of exercise, again, creating more lactic acid. That can be a severe diarrhea. So if we have a lot of diarrhea going on, we lose some of that bicarbonate acid through the feces, through that watery component of the feces. And then renal dysfunction can contribute to that as well. Remember, I talked about the fact that the kidneys have the ability to secrete hydrogen ions into the urine and reabsorb bicarbonate ions in the proximal tubule. So if the kidneys are not working properly, if there's dysfunction of the kidneys, we're going to hold on to excess hydrogen ions if we're not able to secrete them, and we're going to lose excess bicarbonate if we're not able to reabsorb it, and that can contribute to a metabolic acidosis as well. We can also talk about a metabolic alkalosis on the opposite end of the spectrum. This is a disorder where we have excess loss of hydrogen ions or gain of bicarbonate ions. So this is happening, again, any way that has happened, any way that is creating this disturbance that is not involving the lungs, anything other than the involvement of CO2. This can be excessive vomiting, right? The stomach is holding a lot of acid. A lot of these stomach contents is highly acidic. And so vomiting is a way for us to lose hydrogen ions that can contribute to a metabolic alkalosis. Consumption of alkaline products like baking soda, magnesium citrate, which some people kind of drink for like upset stomach, that can also contribute to metabolic alkalosis. So you want to be careful with some of those alkaline products that you may be ingesting. They can be throwing your acid-base balance out of whack. And then finally, renal dysfunction. And a more correct term here would be renal hyperfunction, not so much dysfunction. So you want to get specific here, and maybe you can put this in your notes, renal hyperfunction. So because the kidneys have a natural ability to lose hydrogen ions, right, secrete hydrogen ions into the urine and reabsorb bicarbonate ions across the proximal tubule, if you have an increase in this function or hyperfunction of the kidneys, you can lose excess hydrogen ions if they're secreting too much hydrogen ions, or if you're reabsorbing too much bicarbonate ions, that too many bicarbonate ions, that can also contribute to that metabolic alkalosis. So really a renal hyperfunction would more correctly contribute to this metabolic alkalosis.